In today's video, we will be looking at what's known as extrema, or extreme values. So extreme values is just a mathematics fancy way of saying maximum and minimum values of a function over a certain interval. There are two types of extrema we will study: absolute extrema or global extrema, and relative extrema or local extrema. And in doing so, we will also define what we mean by a critical point of a function. So let's begin with the definition of absolute extrema. And again, there are two of them. There's maximum and minimum. So we let f be a function that is defined over some interval I, and we let C be some point in I. We say that f has an absolute maximum, also known as a global maximum, depending on the text you're looking at, on I at C if f of C is greater than or equal to f of x for every value of x in the interval I. Right, so in other words, f of C is an absolute maximum if it is the largest value that f takes on within the interval. Now that makes sense. For absolute minimum, the definition is almost identical. Right, so this is called an absolute minimum, or again, a global minimum. On I, C, if now f of C is less than or equal to f of x for every value x in the interval. All right, so again, it's an absolute minimum if it is the smallest value that f takes on within that interval. Again, that makes sense. All right, so just to sketch this idea, all right, let's consider this function. And we'll say that this doesn't continue indefinitely, right? So we're going to say these are closed points. Okay. Then this point right here would be the absolute maximum. And this point down here would be our absolute minimum. If we were to change this, and then we were to say this was to continue on forever down that way, and this was to continue on forever that way, right, then that would mean that this is going down towards negative infinity, right? This is going up towards positive infinity. These points would no longer be an absolute max nor an absolute min. However, However, these points are still of some importance, and we will be looking at them very shortly. These would be called relative extrema. However, first we need to look at a very important theorem in the study of mathematics, and this is known, I'm sorry, wrong color. This is known as the extreme value theorem, or the EVT. This says if f is a continuous function over the closed bounded interval a to b, then there is a point in AB at which f attains an absolute maximum over that interval, over a to b, and there is a point in AB at which f attains an absolute minimum over AB. Right? So that is a long fancy way of saying that if you have a continuous function over a closed bounded interval, then that function must have both an absolute max and an absolute min. Now, the actual proof of this is rather technical. We will not be considering it in this series, but the idea has to do with this graph. If we say, I'm going to change this to make this just in the first quadrant. Let's say this is A here, this is B here. Right? If it's continuous, it means it can be drawn right without any kind of jumps, gaps, interruptions. Well, you can see in this interval, the function would have to have a smallest value and a largest value simply because it cuts off at the end, A, B, so it can't go on indefinitely, either in the negative infinity direction or the positive infinity direction. And since there are no interruptions in the graph, there is going to be a lowest point and there is going to be an uppermost point. It could occur somewhere in here in the interval, or it could occur at either of the endpoints. But that is the essence of the extreme value theorem. Let's now study relative extrema. And again, there are going to be two definitions for this. We're going to have one for the relative maximum and one for the relative minimum. So a function f has a relative maximum also called a local maximum, again depending on the text you're reading, at C if there exists an open interval I containing the point C and is contained in the domain of F such that f of c is greater than or equal to f of x for all values x in I. So, in other words, we say that f of c is a relative maximum if we can find some interval that contains c and in the domain of f, where f of c is the largest value within that open interval. And I will sketch this idea. First, we'll write out the definition for local minimum, and just as with the absolute, this definition is practically identical. Now the difference here is such that f of c is less than or equal to f of x, right, for every value x in that interval. And let's just take a look. So let's do something like this. And continue out that way. All right, so we would have oh my. Sorry about that. I don't know what happened there. So we would do, so we have a min, right? So these points here would be relative, or yeah, relative minimum. Because, in a sense, what we can do is we can draw a circle around it, where it is the smallest value within that circle. Right? It doesn't matter how small we make it, or how large we make it. The fact is, it exists. Now, this also happens to be an absolute minimum, right? It is the smallest absolute value. These points would be the relative maxima for the same argument, right? We can draw a circle around these points where it is the largest value. Now, this here happens to be an absolute maximum, right? Because again, it is the largest value within the closed interval. Now what we want to do is we want to take a moment and notice if we draw a tangent line at these absolute minima, notice they all have slope 0, so f prime of x would be equal to 0. Same thing with this point here and this point there. This point, however, is a vertical tangent line, which means f prime does not exist. So the relative extrema appear to occur at points where either the derivative is zero or non-existent. And we have a special name for such points. And these numbers are, as mentioned in the introduction, known as critical points or critical numbers. So we let C be an interior point in the domain of F. We say that C is a critical point or a critical number of F if F prime of C is equal to 0, or F prime of C is undefined. And we'll now formally state our earlier observation. This is known as Fermat's theorem. Which states if F has a relative extrema at C, actually it's extremum at C, and F is differentiable at C, then F prime of C is equal to 0. Alright, and we will actually now go ahead and formally prove this observation. So what we do is we suppose that F has a local extremum at C, and that F prime of C exists. That is, it's differentiable at C. What we need to show is that F prime of C is equal to 0. And how we do this is by showing that F prime of C is greater than or equal to 0 and also less than or equal to 0, right? If a value is both greater than or equal to 0 and less than or equal to 0, then it has to equal 0. Now, since F has an extreme value at C, F has either a relative max or a relative min at C. What we're going to do for this proof is suppose that F of C is a max. The proof of min is identical, so it'll be left to the viewer, right? Since F of C is a relative max, there must exist an open interval I containing C such that f of C is greater than or equal to f of x for every value of x in I. But f is differentiable, right? So f prime of C is equal to the limit as x approaches C of f of x minus f of C over x minus C. Now, this limit must exist. So this means that f prime of C is equal to the right-handed limit at C and f prime of C has to equal the left-handed limit. Now, f of C is a maximum. So since f of C is a max, f of x minus f of C is always less than or equal to 0, right, for all x near C. What we notice then is this first limit. Is going to wind up giving us a negative over positive, so this has to be less than or equal to 0. And the second limit gives us a negative over negative, right? Because since x is to the right of C, x minus C will be positive. X is to the left of C, x minus C will be negative. And f of x minus f of C is always negative. Right, therefore, we've now just shown that f prime of C is less than or equal to 0 by the right-hand limit, and f prime of C is greater than or equal to 0 by the left-handed limit. That is what we needed to show. And so, Fermat's theorem has now been proven. We will now look at a couple examples of finding extrema. We will first consider the function f of x equals negative x squared plus 3x minus 2 over the closed interval 1 to 3, and we want to find all of the absolute extrema. Right, first thing we do is take the first derivative, that is negative 2x plus 3. We want to find all the critical numbers of f. Right, remember, that'll be wherever f prime is undefined or equal to 0. Well, f prime is defined everywhere in this case. So all we have to do is set this equal to 0 and solve. This will give x is equal to 3/2. This is our critical point. Now, as a direct corollary of Fermat's theorem, we know that the extrema will occur at either critical points or the endpoints of a closed interval. So what we now do is we create a table. The x values will be the endpoints as well as the critical points. Then we just evaluate f of x at all those points. F of 1 is 0. F of 3/2 is a quarter. F of 3 is negative 2. The largest value is our absolute max. That occurs at f of 3/2, which is a quarter. And our absolute min is the smallest value. This occurs at f of 3, which is -2. So these would be our absolute extrema for this function. And as a final example, we'll do the same thing now for the function x squared minus 3x to the 2/3 over the interval 0 to 2. Again, first thing we want to do is find critical points, so we have to take the first derivative, 2x minus 2x to the minus third. That is 2x minus 2 over x to the 1/3, which is 2x to the 4/3 minus 2 all over x to the third. Now, f prime of 0 is undefined. And 0 happens to be in our interval. If we were now just to set f prime of x equal to 0, then 2x to the 4/3 minus 2 equals 0. This would mean that x to the 4/3 has to be 1, or x itself has to be 1. So we have two critical points. X equals 0 and x equals 1. However, 0 also happens to be an endpoint, right? So there's actually still only 3 numbers we have to test. X equals 0, x equals 1, and x equals 2. Right? F of 0 is 0. F of 1 is -2. F of 2 is 4 minus 3 cubed root of 4. Absolute max and absolute min. The only hiccup is that 4 minus 3 cubed root of 4. So let's go ahead and take a look at an approximate value for that. Minus 3 times cube root of 4. Let's put a decimal to get an approximate answer, and it winds up being about -0.7. Right, so if we look here, 0 would then be the largest value. And then -2 would be the smallest value. And that concludes this video on extreme values. What we will do in the next video is look at increasing, decreasing. So we'll review what it means for a function to be increasing and what it means to be decreasing. And we will develop a way to determine where a function is increasing and decreasing by using its first derivative. So I will see everyone in the next video.